Okay, let's look at another two-tailed hypothesis problem. And as you'll see, this is completely different than the one I had before. Consider the normal population of hours spent grading among college professors. Mu is 14, standard deviation of 8. A sample of 4 professors at private colleges shows a mean number of hours grading of 21.6. We hypothesize that private college professors grade a different number of hours. So what are the null and alternate hypotheses for a two-tailed test? And again, it's the same thing. The mu grading time among private college professors, it's going to be different than 14 according to the alternate, but the same as 14 according to the null hypothesis. It doesn't make any difference that it's private versus, say, other professors, the default universe of professors. So, I write extensively in these subscripts, but it's just sort of a marker. It's a way for me to keep track, if you will, of what this proposed universe of people or entities looks like. Now, again, it's alpha of 05 right here, as you can see. And I'll do the same as I did before. And normally I wouldn't have the green part there, but I just got ahead of myself a little bit. Establish the critical boundaries on the distribution of sample means according to HO. Fine, will do. Plus and minus 1.96. And you can see, I'm going to do the math here. A sample of 4 professors at a private college shows a mean number of hours grading of 21.6. So the first thing I have to do is, from the problem, it said that there was a standard deviation of 8. So I'll plug that in, divided by the 4 professors. 8 over 2 is 4. And then plug that into the Z formula. So 21.6 hours among those private college professors minus 14 is the default. And then divide by 4, and what that's going to give me is 1.90. Now, where does that fall? Again, we fail to reject the null hypothesis. We didn't quite make it, although you can see how incredibly close it was. My gosh, it really was a close call. But nonetheless, that doesn't bring any angst on the researcher. Couldn't care less. If it's 1.90 in a problem like this, we're going to fail to reject. It's a binary outcome, just like whether whether or not you owe money at the airport if your bag's overweight. So, same thing. There's no further decision to be made. Now, again, what happened here? Because this 21.6, my gosh, looks a whole lot different than 14. That's pretty far apart. But what undercut this problem was the N of 4 again. And honestly, I don't know why I picked 2 problems with such a low sample size. But in this case, a rather large effect of 7.6 hours, quote-unquote effect, since this is a quasi-independent variable, did not yield statistical significance because the low sample size sort of served as an enemy of sorts. Now, we'll get a contrary example here soon in which there's a very large sample size and the precise opposite outcome happens. But for our purposes, let's not get preoccupied with that. Just bear in mind the expression. I hope you understand where these subscript phrases came from. I'm speculating about the number of grading hours among private college professors. If it's the same as the default, the normal 14, then I would say, well, the mean grading time among private college professors is 14. If it's different, and it could be less or it could be more in these two-tailed hypotheses, in that case, it'd be not equal to 14. Same thing. I set my goalpost up. In this case, it happened to be the same as the last problem with alpha of 05 two-tailed. And we remember where that came from before, by the way. Let's go to the previous problem. This thing right here. Remember where that the origin of where we got 1.96. Then I compute my z-score precisely as we did in Chapter 7, just inputting the things that we know to be true from the problem, and then graduating onto the z-score. And sure enough, I just look at an ocular comparison. In other words, just look at it. In this case, 1.90 is not outside these boundaries that it would have to be for me to reject the null hypothesis. So therefore, I'm going to fail to reject it. And this is another case where I'll say that this sample mean was not particularly unlikely to have been obtained given that the null hypothesis was true. Therefore, I am not going to reject the null hypothesis. Now, both of these new problems that I've introduced stand in contrast to the one that we had before. Back in old-timey days, when we were making this decision about the red T-shirts, in this case, 16.7 versus 15.8 with that standard error of 0.4. In this case, it exceeded it. And in that case, I'm rejecting the null hypothesis. Now, what's a subtle difference between these problems? You'll remember in this problem, that had to do with the t-shirts, they had a much larger sample size. And the advantage of that was that I'm dividing by a larger number on the standard error, which has the effect of exploding the z-score. So all things equal, a larger sample size does leverage in favor of the researcher, allows it for them to be more likely to reject the null hypothesis. But in these two most recent problems, and I don't want to say unfortunately, it just is what it is, we fell short by some margin. And even though this is close, we're still going to fail to reject the null hypothesis. And, you might qualify it in the paper that it was close to significant, but nonetheless, you kind of have to confess, if you will, that you didn't reach statistical significance.